since I already talked about how wonderful it is to be here before the recording was started, let me skip that and get right to the point. So I want to talk a little bit about geometric separators and their algorithmic applications, which is work I did in the past couple of years with a number of people, well, who I will also mention later on. But before I get to that, I want to talk a little bit about the background and context of the work. So here you see the way I was looking at the world as an algorithms person, well, let's say until 10 years ago, and that's as follows. So when I get an algorithmic problem, then I decide, or I try to decide, can I solve it in polynomial time or not? Right, so maybe I actually show that it's NP hard, so you cannot expect to solve it in polynomial time. And if that's the case, then maybe you try to give an approximation algorithm. Or if you're lucky, then the problem actually is solvable in polynomial time. And then you try to find the fastest possible algorithm, right? So maybe first n squared, and then you want to see whether you can do n polylog, and then n log n, and so on, right? And then sometimes when the problem is rather easy, like convex hull, you can actually prove maybe that you cannot do it faster than n log n. So sometimes you also get lower bounds. Okay, well, I should not say recent years, but let's say the past decade, or maybe even a little bit longer already, people started to look into this complexity thing in a little bit more detail. So for instance, if you know that a problem is NP hard, then you don't sort of give up on exact solutions and resort to approximation, but what you can do is you can study parametrized complexity. In that case, you not only analyze the running time of your algorithm as a function of n, the number of objects, but you introduce a second parameter, which, well, if you're lucky, can be smaller than n, and then try to come up with an algorithm whose exponential behavior only shows up in the second parameter and not in the input size n. The other thing that people did, and that's actually what we're also going to see in this talk, is to look at so-called sub-exponential algorithms, right? And those are algorithms that they are not going to be polynomial, because this is for NP hard problems, so we cannot expect that. But they are faster than 2 to the n. And I'll say much more about that in a moment. Okay. The other thing that people also do is maybe even for problems that you can solve in polynomial time, right? If, let's say, you can solve the problem in n squared time, and you wonder, can we do faster? Well, even if you cannot prove lower bounds, then you might relate the problem that you have to another problem via some sort of reduction, and then say, well, if this problem cannot be solved in, let's say, subquadratic time, then this other problem cannot be solved in subquadratic time either, right? So you get conditional lower bounds. And of course, you know, we're kind of used to conditional lower bounds anyway, because my statement that NP hard problems cannot be solved in polynomial time, that's of course conditional to the statement that P is not equal to NP. Okay, so that was my mini introduction to, let's say, the complexity theoretic background of what I'm going to tell you. So the rest of the talk, here you see the outline. So first I'm going to talk a little bit about sub-exponential algorithms for classic problems on planar graphs, right? And this is all relatively old. Then I'm going to talk about sub-exponential algorithms for disk graphs, and that's where the new stuff comes in. Then I'm going to hopefully say something about Euclidean TSP, and, well, maybe also something about lower bounds for that. Okay, so let's start with the planar graphs. So, well, as I said before, if you, well, previously we were happy to say that something is not polynomial, but now we're going to look into this in more detail, and we're going to wonder, are there algorithms, well, that are maybe not polynomial, but at least sub-exponential? So that means that the running time is 2 to the little o of n, right? So for instance, 2 to the order square root of n, or maybe n to the square root of n, right? You have to think a little bit about it, but of course this n to the square root of n is 2 to the square root of n log n, right? So that's also 2 to the little o of n, or maybe 2 to the n divided by log n. So something like that. So now you can of course wonder, well, if something is NP hard, is it actually possible to do this? So let's look at one of our basic NP hard problems, 3-SAT. Okay, so here the question is, you have this 3CNF formula, right? So as one you see on the slide, and you ask yourself, is it satisfiable? So of course, what you could do is simply, if you have n variables, try all 2 to the power n possible settings of your variables and verify is the formula true or not. But you wonder if you can do faster. And actually, the answer is no, or at least the hypothesis is no, because there's well, this result, or result hypothesis, I should say, by Impagliazzo, Paturi, and Zane, that says that there is no sub-exponential algorithm for 3-SAT, right? So you cannot solve 3-SAT in 2 to the little o of n. Okay, so this exponential time hypothesis, ETH, is, well, it's, I guess, for p is not equal to np, almost everybody believes that it's true. This, I would say, probably most people believe that it's true, although I'm not a complexity theory person, so this is a little bit of a guess. There's also a version which is called the strong exponential time hypothesis, where I think probably, well, maybe there are a little bit more people who believe that that may not be true. But anyway, this exponential time hypothesis is a established hypothesis that I guess most people believe. So under this hypothesis, for 3-SAT, there's not much we can do, right? There's no sub-exponential algorithm. So let's look a bit at some other problems. So for instance, independent set. Okay, I give you a graph. You want to find a set of nodes with no edges between them, an independent set that is as large as possible. Okay, or another classic problem, vertex cover, right? Find the smallest set so that for every edge you have at least one of the endpoints in your set. And of course, these are just the complement of each other. If you have a minimum vertex cover, then the complement is a maximum independent set. Okay, another classic problem is dominating set. So here again you have a graph, and now you want to find a minimum size vertex set such that every vertex is either in this set or it has a neighbor in the set. Okay, so these are all well-known and nice and NP hard graph problems. So if we cannot get sub-exponential algorithms for 3-SAT, maybe we can get sub-exponential algorithms for these kind of graph problems. Well, bad news, not possible, right? So assuming this exponential time hypothesis, you cannot get sub-exponential algorithms for these classic problems. So it seems that there's maybe not much possible, but actually, as soon as your graphs are planar, then suddenly you can do many things. So each of these classic problems can be solved in sub-exponential time on planar graphs. So what I want to do next is, first of all, explain a little bit about how you do that. And it's actually quite simple. It uses the planar separator theorem. And after that, I want to talk about how you can also get sub-exponential algorithms for geometric graphs, certain geometric graphs, and that will require well, a generalization of the planar separator theorem that is actually quite nice and powerful. Okay, so how can we solve these problems on planar graphs in sub-exponential time? Well, it uses the planar separator theorem. So what's that theorem? So here you see a planar graph, right? A graph where the edges do not cross, or you can draw it in such a way that the edges do not cross. So the planar separator theorem says that I can find a small subset of my nodes, okay, which I call the separator, such that if you remove those nodes, now the remaining nodes can be partitioned into two subsets, A and B, that each have at most 2/3 n of the vertices, right? So it's kind of a balanced separation. And the number of nodes you have to remove is only square root of n. Right, so here's a picture. I have a small set S, or the square root of n nodes, such that removal will disconnect the graph, or let's say I have no edges from A to B. And the sets A and B each have at most 2/3 n of the vertices. So, well, and yeah, I forgot to mention, but you can also actually compute such a separator very quickly. So how can we use this to get sub-exponential algorithms? So let me illustrate this for independent set, where it's actually trivial to do so. And the algorithm is as follows. So in step 1, we compute such a separator, right? It's balanced and it has size square root of n. Okay, what do I do next? Well, I'm going to guess, you could say, all possibilities of how my maximum independent set intersects with the separator. Right, so this my solution will have 0 or more vertices in the separator. So I'm going to guess which one those are. Or maybe I should say I'm going to try all options. Okay, and then for each of my guesses, I'm going to solve the problem recursively. That's sort of the idea. So here, okay, this is an independent set. I'm going to try what happens if I take this one, or I'm going to try this or this one, and so on. Okay, so I'm going to try all possible independent sets in my separator, right? Because a global independent set, the vertices inside the separator should obviously also be independent. And well, for this guess, what I'm going to do, well, let's say on the left side, I'm going to solve my problem recursively. So I'm going to find a maximum independent set there. But of course, I can no longer use the vertices that are adjacent to the nodes I've guessed in the separator. So I simply throw out these nodes and then recursively compute a maximum independent set on the left in A. Okay, I do the same thing in B. And what I get now is the maximum independent set under the condition that I have these specific two nodes, this specific independent set from my separator. Okay, and then of course, well, I get this is the solution for this guess. I do that for all the guesses, and I take the best one overall. Okay, I hope it's clear that that this gives an optimal solution. So all that remains is to analyze the running time. By the way, I realized that I have not been monitoring the chat, but I see now that there's nothing in the chat. So if you have any questions or you want to interrupt me, you can either just speak up or put something in the chat, and that's also fine. Okay. So what is the running time of this algorithm? Oops. Well, here you see the recurrence. Remember that the separator has order square root of n nodes. So, well, for each one of them, I can either put it in my separator, or sorry, in my independent set for the separator or not. So the number of choices is 2 to the square root of n. Okay. For each of these choices, well, I actually solve 2 subproblems, right? One on the left and one on the right. But of course, this extra factor 2 that's simply here hidden in this 2 to the order square root of n. Well, I maybe have some overhead to generate the independent sets of the separator, but this is the recurrence I get. And if you analyze what comes out, you have 2 to the square root of n. Okay, and of course, the constant in this big O here is going to be slightly larger than the constant in this other big O. But this is the solution that you get. Right, so this is a sort of trivial algorithm using this very nice planar separator that gives a sub-exponential algorithm for independent set. And maybe I should also mention, you can wonder, well, this was actually pretty straightforward. Maybe you can do better than 2 to the square root of n, right? Maybe 2 to the, n to the 1/3. But actually, again, assuming the exponential time hypothesis, this is not possible. Okay. So the next thing is I want to show you a very nice geometric proof of the planar separator theorem. And the reason I'm showing it is that the more complicated separator theorem for geometric intersection graphs that I will show later, the proof of that is kind of similar to the proof I'm going to explain now, but a lot more tricky. So, well, with this proof, you have some of the basic ideas, and then if you want to know for the other planar separator theorem how you prove it, I guess you have to read the paper. But let's have a look at the planar separator theorem. So I guess all of you know that I can draw or realize any planar graph as the contact graph of a set of interior disjoint disks. Right, so here you see a picture. On the left, you see a graph. On the right, you see a set of disks. There's a one-to-one correspondence between the nodes in the graph and the disks. And 2 nodes are connected if and only if the 2 disks are touching. And this is always possible. It's a famous result. So the proof idea is to take this set of disks, this geometric representation, and now to show that there is a square, the red square here, such that the number of disks strictly inside and strictly outside is going to be at most, well, not 2/3 of n, we will get a slightly different constant, but at most a fraction of n. And the number of disks intersecting the square is going to be square root of n. Okay, and obviously, if my separator contains all the disks that intersect the square, then a disk, inside it will not touch any disk that is strictly outside. So indeed, this separator will separate the two sets. Okay, so here's the proof, and it's actually relatively simple and then very nice, I would say. So yeah, maybe I should mention there's a number of people that the proof is not by me or in one of our papers. There's similar proofs have been given before. I guess Sariel Harpelet and Kanroot were maybe well, they definitely had also had this proof, or a slight variation of it maybe. So the proof is as follows. So I'm going to take the smallest square that contains at least n over 37 disks. Okay, and for now, I don't worry about how much time it takes to compute the separator. I just want to show you an existence proof. Okay, so I'm going to take this smallest square, that's the inner one, and I'm going to blow it up by a factor 3, that's the outer one that you see. And now I'm going to draw square root of n squares, as you see in the picture, the red squares, that are a distance 1 over square root of n from each other. Okay, where what I did is I scaled the whole thing such that the inner square, this inner black square, has edge length 1. Okay, so I have square root of n of these red squares, and I want to argue that one of them is a nice separator. Okay, to do that, there's a small technicality. I'm going to distinguish between large disks whose diameter is at least a quarter, right? So they're quite large compared to this square, and the small disks. And somehow we'll see that the large disks, it's nice if we can sort of disregard them at some point in the proof, so they're going to be treated slightly differently. So my separator construction is as follows. Of all of these square root of n squares, I'm going to select one that intersects square root of n of my small disks. Okay, of course, I have to argue that this is possible, but that's the square that I will take. Then I'm going to put all the disks intersecting this sigma I, I'm going to put them in my separator. Okay, now I've separated the things inside the sigma I from the things outside. My separator will consist of everything that is intersecting the sigma I that I selected. And well, for convenience of the proof, I should say, or maybe for convenience of my proof, I will add all large disks intersecting this sigma I or inside it to the separator as well. Okay, so it's going to look something like this, right? So all the dark disks are going to be in my separator. And as you've seen, I also put some of them that are completely inside my red sigma I. I also put them in the separator. It's not really necessary here, but for the generalization, this would be necessary. Okay, so why does this work? Well, we need to check 3 things. The size should be okay, right? Or the square root of n. It should be balanced. Okay, and well, I started by saying I take a square that intersects only square root of n small disks. I should check that that actually exists. So that the size of the separator square root of n is trivial. By my choice of this red square sigma I, it intersects only square root of n small disks. The number of large disks, well, they are large, they're meaning that their diameter is a constant fraction of the size of my red square. Okay, they are disjoint, right? Because we look at disks that are disjoint, or at least disjoint interiors. So by a simple packing argument, there cannot be more than a constant. Okay, so this is easy. Why is it balanced? Well, I claim that it's, well, not 2/3, 1/3, but 36/37 versus 1/37. That's the worst balance I get. So why is this the case? Well, by choice of my inner black square, there are at least n/37 disks inside. Okay, so that means that obviously I have at most 36/37 and this outside. Okay, so that's good. I cannot have too many things outside, but how many things inside can I have? Well, I claim that no matter which of these red squares I take, and even if I would take this outer black square, there cannot be more than 36 n/37 disks inside. Okay, why is this? Well, I partition this outer black square into 6 by 6 smaller cells. Okay, and now take a disk that lies inside the black outer square, right? It's going to intersect one or more of these grid cells. Let's say this blue grid cell here.
Hi.
And
I'm sitting in a seminar, but I'm going to leave.
Oh. Okay, and well, if it's remember that I already put all the large disks, well, larger than 1/4, into my separator, so I don't have to worry about them. But the small ones, if a small disk intersects this blue, dark blue cell here, then it must lie completely inside this slightly inflated light blue cell. But that cell is exactly the same size as this inner black square here. That inner black square was, well, the smallest one, containing at most n/37 disks. So inside here, I cannot have more disks than that. So, well, I have 36 of these cells, each containing at most n/37 disks. So that's it. Okay, so the final thing is I claimed that, well, there's one of these red squares will intersect square root of n disks. Why is this true? Why does such a sigma I exist? Well, if I count the total number of intersections between disks and squares, okay, well, here I can count that as follows. I take the sum over all my disks. So I equals 1 to, well, it's not n because I only have to worry about the small disks, but that's not, doesn't really matter. So it's the sum over all the disks. How many squares can a disk intersect? Well, remember that the distance between two of these red squares is 1/square root of n. So if the diameter is, let's say, smaller than that, it can intersect only one square. If the diameter is maybe 2 times 1/square root of n, it can intersect 2, and so on. right? So in general, you get that the number of red squares that you intersect, it depends on how large the disk is. And the number that you get is this diameter times square root of n. Okay. So that means if I rewrite the sum, I simply get a linear term plus square root of n times, well, the diameter, which is the square root of the area, right, roughly, or it's at most. So that is actually linear. So why is it linear? Well, we only have to worry about, or I have to show that this last summation here is square root of n. And well, that's again some kind of packing argument that uses that all disks lie inside this bounded, well, not quite inside this thing. They might be sticking out a bit. They might be sticking out a bit out of this larger square. So they don't lie in an area of size 3 by 3, but because they're small disks, well, there's maybe a quarter here and a quarter here, it's 3.5 squared. And then using that, you can show that, well, this here cannot be more than square root of n. Okay, but let me skip the, if you look, probably if you look at it for half a minute or something, you will see that this is true. Okay, so this was hopefully a nice geometric proof of the planar separator theorem. Wait, I forgot the last line. Of course, if the total number of pairs of disk square that intersect is linear, and I had square root of n squares, okay, if the total is linear and I have square root of n things, then one of them, at least one of them, must intersect at most square root of n disks, right? Because the average number of intersections is square root of n. So that was this. So let me maybe speed up a little bit and now go to disk graphs. So what I want to do is I want to generalize the previous results to disk graphs. So these are graphs where, again, the nodes are disks, right? Like in this geometric representation of planar graphs. But now the disks are not interior disjoint, they can intersect each other. Right? So the nodes are disks and two nodes are connected if the corresponding disks intersect. And well, if all the disks have exactly the same size, the unit disks, then these graphs are a popular model for wireless networks, where you say, okay, the centers of the disks are now wireless devices that can communicate when they're a distance at most 1. Right, and distance at most 1 would be that the radius 1/2 disk centered at 1 intersects the radius 1/2 disk centered at the other. So these intersection graphs for unit disks have been studied quite a lot. So would it be possible to get a balanced separator of size square root of n for these kind of disk graphs? And probably many of you already realize this is not going to work, right? Because I can have an arbitrarily large clique. I can just put all the disks on top of each other, and then there's no way that you can get a separator that is small and that separates the graph into two balanced pieces. So it seems that, okay, if you want to do any kind of sub-exponential algorithms for disk graphs, you're going to need a different mechanism than using separators. But actually, this is not the case, because what you can do is the following. And so here I get to the more recent work. So a paper with Hans Botlander, Sándor Kisfaludi Bak, my former PhD student, who is, I guess, was one of the driving forces behind all this. Daniel Marks and Tom van der Zande. So here, the statement is as follows. So again, we're going to have a separator that separates the nodes of my graph into two subsets of at most a fraction of the nodes. Right, so again, it's going to split, well, there's 36 over 37. But now I'm not measuring the total number of nodes, or if you think about them as disks in a disk graph, the total number of disks that I put into my separator. But I view this separator as consisting of cliques. And now I want to put not few nodes in my separator, but few cliques. Okay. Actually, the result that we need is going to be slightly different, because for a clique, I don't pay a cost of 1, but what I pay is the logarithm of the size of the clique. Okay, so the theorem is, and the proof is inspired by the proof I just showed you for planar graphs, but more complicated. The theorem says that I can find in a disk graph, right, represented here by, okay, I have these disks and I connect two things if they intersect. I can find a collection of cliques that such that the stuff inside and the stuff is at most a constant fraction of n, and the stuff outside is a constant fraction of n. And the size of my separator, where with size I actually mean the sum of the logarithm of the sizes of the cliques, right? That is square root of n. Okay, so what I want to show next is that with this separator, I can now get a sub-exponential algorithm for independent set on disk graphs. Okay, so how does it work? Well, exactly the same as before. I compute this separator, and then again I'm going to try all possible ways in which my solution will interact with the separator. So that means all possible independent sets in my separator, and then recurse on the left and on the right side. Okay, so it's the same as before. And why does it work? Well, the crucial thing is, what is the number of guesses for our independent set? We used to say, okay, the separator has size squared of n. So obviously the number of different subsets that I have to guess is 2 to the square root of n. Now my separator can have a linear number of disks, but they come in cliques. And obviously from a clique, you can pick at most one thing in your independent set. So from a clique CI, I have only CI plus 1 different choices, right? I can pick no vertex, or this vertex, or this vertex, or this one, and so on, right? So you pick either a single vertex or no vertex. So the number of ways in which you can do that is CI plus 1. And then, well, you have a number of cliques. So of course, from each clique, you have now CI plus 1 different options. So the total number of options is the product. Okay. Rewrite. Well, this is 2 to the log that. And then the usual trick, I replace this product by 2 to the power the sum. And now in this exponent, you see the weight of my clique-based separator, right? The sum of the logarithm of the clique sizes was order square root of n. So with the same sort of trivial algorithm, this all works out nicely. Okay, so the running time is 2 to the square root of n. So if you also want to do different problems like dominating sets, it becomes more difficult, And here, actually, we can only do it for unit disk graphs. And the crucial property is that if you think about a unit disk graph, then our cliques are going to intersect, and that's because of the way we constructed them, only a constant number of other cliques. Okay, that's just a property of our way of doing it. And of course, that means that a dominating set has to select only a constant number of disks from each clique. Right? So if you pick one, you already dominate that clique itself, and maybe you need one more for each of the other cliques, but that's, well, if you would pick more, then it would have been better to pick something from these neighboring cliques. So this is the crucial property. And then again, if you simply write down the formulas that you get, you again see that it's 2 to the square root of n. Okay. So we can do all these problems using a general framework for unit disk graphs in 2 to the square root of n time. So again, we use the separator theorem, and now it becomes a little bit more complicated, but the basis is again using this clique-based separator. Okay, here you see the same theorem, but now in higher dimensions, right? So instead of having disks in the plane, you can do the same thing for ball graphs in 3D or in higher dimensions. And well, what you see is that this square root of n that you got, right? The square root of n was for the well, sum of these weights of the cliques, now becomes n to the 1 minus 1 over d. And if you think about it, then you can see that this is actually going to be tight. So why do we get this bound? Well, if I put my disks essentially in a grid like this, then you will see that any balanced separator is going to have this size. Right? Somehow you need, if it's balanced, then the number of disks inside should be linear. I mean, that's one way to think about it, but then the number of things on the boundary that sort of you need to separate from the rest is going to be this n to the 1 minus 1 over d. Okay, and yeah, all of these results are actually optimal if you believe the exponential time hypothesis. Well, let me skip this here, and in the remaining time, there's not that much. I want to briefly talk about
we have a little bit more time because we started kind of late. So
okay, so let me use a little bit more time, but well, we'll see. If I see people leaving the Zoom, then I realize that it's time to stop. Let's put it that way. So Euclidean TSP. Well, I guess everybody in the audience will know what TSP is. I want to visit a given set of, let's say, cities using a minimum length tour. And well, there's applications in well, maybe when you want to deliver packages, but also in drilling holes on a printed circuit board and so on. So there's two settings. One is the purely graph theoretic setting, right, where I have a weighted graph. And well, let's say you may be satisfying the triangle inequality, or you could also look at settings where this is not the case. And now I want to have a shortest tour in this graph, minimum weight. What I'm interested in is the Euclidean setting, where the cities are points in the plane, and the edge length is the Euclidean distance. Okay, so well, there's this famous algorithm by Held-Karp and Bellman that uses a clever dynamic program to solve it in 2 to the n time. So that works for the general case. For the Euclidean case, until recently, and that's what we wanted to improve and what I'm going to talk about a little bit, the best thing was n to the square root of n. Okay, or in other words, 2 to the square root of n log n. And the question was, can you get rid of the log n in the exponent? Okay, and well, the result is yes, you can, but you cannot do better than that, right? So you can get 2 to the order square root of n, but not 2 to the little o of square root of n. So maybe first of all, let me hand wave the proof that you cannot do better than 2 to the order square root of n. And the hand waving is, it's going to be major hand waving. And the only thing that I want to convey is sort of the message, how you can prove something like that and where the square root of n comes from, and how that relates to the exponential time hypothesis, because that's 2 to the little o of n. So what happens is the following. So here you see a construction, that a reduction that takes a 3-sat instance and translates it somehow to a Euclidean TSP version, right? So here you see at the top, you see variable gadgets, and here you see some clause gadgets, and then you see these wires, and actually when 2 wires cross, there's some crossing gadget and so on. Okay, so if you do this, because of this crossing gadget, the original instance, which had maybe a n variables, and let's say also n clauses, now because of this crossing gadget, I suddenly maybe have n squared points in my TSP instance, right? So this little variable gadget probably has a constant number of points. This also has constant number of points, but for every crossing, I also need something. So in total, I get n squared points. And if you prove that something is NP hard, okay, you're happy if your reduction is polynomial and you don't care so much about exactly, you know, how polynomial, so to speak. But here, the fact that you blow things up from n to n squared, that's where this square root of n in the exponent shows up. Because now what I can say is, okay, apparently if this everything works here, if I can solve Euclidean TSP using this thing, I can now solve 3-sat. But actually, if you look at it more precisely, if I can solve Euclidean TSP on n squared points, I can solve 3-sat on n variables. So that means that to contradict the exponential time hypothesis, okay, I have to solve 3-sat in 2 to the little o of n, but then I have to solve TSP in 2 to the little o of square root of n. Okay, so this is how you get these well, conditional lower bounds of the form 2 to the square root of n. Okay, so that was the lower bound. How do we get the upper bound? Well, the main tool is another geometric separator theorem. So what I want is something like, okay, I take my optimal tour and I argue that there's a separator that is crossed only few times by the optimal tour. And then, well, somehow work recursively on the inside and on the outside. So first of all, I claim that such a separator exists, right? Note that I don't know the tour, so it might be a bit tricky to actually compute it, but I want to argue that at least it exists. So why does it exist? Well, if you look at something like this, then obviously this cannot be the optimal solution, right? If things are far apart, like here, you're not going to be going back and forth many times, because then you can shortcut. So what you can show is that the edges in this tour have, and originally this was called the packing property, in completely different context, it's called low density, right? But the property of the edges in an optimal tour is that if I take a square, any square, and I look at all the edges of the tour that intersect the square and that are larger than the square, then the number of such edges is a constant. I cannot have many long edges intersecting this square, because then I can shortcut. Okay, you have to prove this, but this is intuitively, it's believable that this is true. Once you have a set of objects that has low density, then you can show that there's a good separator for it, right? And actually, original papers on Euclidean TSP, they already had such a separator. So here you see some of those papers. So suppose I have this separator, then what do I do? Well, first of all, I only know the existence of the separator. And if I knew the solution, then I have my low density set of edges and I can compute the separator, but I don't know the solution. So I'm simply going to try all possible separators and hope that they're good separators. Right, so since my separator, I know that I can get it using a square, I simply try all possible squares, essentially. Right, and of course, I only have to look at combinatorially different squares where the points inside and outside are different. So the number of such squares is n cubed. So I'm going to try a polynomial number of different separators. Okay, for each such separator, I'm going to say, well, suppose that this would be the optimal or the real separator that I want. Well, then I know that it's crossed only square root of n times. Okay, so let me simply guess the edges that are crossing this square. So I'm going to guess a subset of square root of n edges and assume that these are the edges of my optimal tour. Right, so I'm going to do all these guesses. Of course, I've n squared edges from which I have to choose. Okay, I choose square root of n of them, and I make all possible ways of doing that. Okay, of course, some I can immediately discard, like if I have a subset where a point is incident to 3 edges, that doesn't make sense, and so on. But the total number of options that I have to check is at most n to the order square root of n. Okay, then once I have guessed the things that are crossing the separator, I'm going to recursively solve problems inside and outside. And this is going to be, well, it's not really a recursive call on TSP, because inside and outside, you're now no longer searching for a tour, right? Because I already have these things crossing. And what you actually have is that what is going on inside, together with what is going on outside, these solutions together with the crossing edges, they should form my tour. So the subproblems that we're dealing with are sort of a generalization of TSP, where instead of finding a tour, you want to find a set of paths that realize a certain connection pattern. And here there's more guessing going on, because for the inside, I have to guess what is happening on the outside, because depending on that, different connections have to be made on the inside, right? I want the total to be a tour. So if I on the outside do this and this, that would be different than from the outside. I do this and this, right? Because some of these things simply don't match up. You don't get a tour, but you get a number of cycles. So for the subproblem on the inside, I have to guess the connectivity pattern that is realized on the outside by the optimal solution. And for that connectivity pattern, I now have to solve my subproblem inside. Okay, so this is the way it works. And now the running time is, well, here, step one, I'm guessing n cubed different separators. For each separator, I'm guessing n to the square root of n sets of crossing edges. For each of these things, I'm going to guess all of these connectivity patterns. Okay, if I multiply this, I simply get n to the square root of n with a slightly larger constant. And this is the recurrence I get, right, where this delta is going to be my balance factor of the separator. So this is what you can do. And now, well, as I said, what we really hope for is 2 to the square root of n and not n to the square root of n. So the way to do it is to actually prove a new kind of separator theorem, which is a separator theorem for points. So initially we completely forget about the tour, and I just want to do the following. If you look at this picture here, right, remember that the optimal tour has low density. So you don't have all these edges like this that are pretty long crossing from inside to outside. So in some sense, points that are really sort of in the middle near the center of the square are pretty safe because we're not going to have many edges to the outside. What is dangerous is what you see here. If I have lots of points close to my separator on both sides, because then my TSP tour could be crossing many times. So intuitively, you could say something like, okay, I want only square root of n points close to my separator, and most of the points really on the inside near the center of the separator. Well, what you actually need and can get is something like this, where, well, if I look at this annulus around my separator, then the number of points inside this annulus depends on the width of the annulus, right? So the number of points at certain distance is at most something. Okay, this turns out to be sufficient and also what we can prove. So using this, we can show that, well, we have a balanced separator that's crossed at most square root of n times. But by itself, this is, well, nice, but we already had this. So what's the point? Well, the point is that the number of ways in which we have to guess how the separator is being crossed by the tour, that now reduces from n to the square root of n to 2 to the square root of n. Because for things going really from the sort of middle of the square to outside, there I don't have to guess, you know, many subsets because there's only going to be a constant of them. And if you then, you know, look at this previous thing and then, well, with some care, let's put it that way, you can argue that this is the case. So now, well, this is now with a new separator only 2 to the square root of n. Well, this was still n to the square root of n. So that's another problem you have to deal with. There's two ways of doing it. One is something that perhaps some of you already realized, that this connectivity pattern on the outside that you have to guess, right? Because in 2D, the TSP doesn't cross itself. These things, you get some kind of Catalan structures going on, right? That's some bracketing structure. So that works. If you want to do it in higher dimension, you have to do some other stuff. So, well, using that, we can show that in the plane, you can solve things in 2 to the squared of n time. It extends to high dimensions. And, well, there's no algorithm that can do better than this, assuming the exponential time hypothesis. Okay, so the summary. So first of all, we've seen this clique-based separator, right? So if instead of a planar graph, you have a geometric intersection graph, and it's a geometric intersection graph of disks, or maybe convex fat objects, then you can find a separator where the sum consisting of cliques, where the sum of the logarithm of the clique sizes is only square root of n. Right, and well, I showed you how to use that for independent sets, but there's other things you can do with it as well. There's this distance-based separator for points, right? You can find a square such that you don't have too many points that are near the square, which we used for Euclidean TSP. Well, all of this generalizes to high dimension. Some recent work that we did was, well, what happens if I generalize even further? Right, I started with planar graphs, or in other words, graphs of touching disks. Then I went to intersection graphs of disks, so the disks could intersect. But now what if you have pseudo disks? Okay, actually, we don't really know. We know that we can still get this clique-based separator, but instead of square root of n, we can only prove n to the 2/3. Or if instead of disks, I give you geodesic disks inside a polygon, and I look at the intersection graph of the geodesic disks, what can you do? Well, again, we get this n to the 2/3. And we also had some other results. Okay, so I guess this was it. So as I said, this was work with a number of people that you see here, and maybe especially pay attention to this guy's name, Shandor. He used to be my PhD student, was really great, and I guess much of what I've been talking about is also due to him being a PhD student in Eindhoven. So thanks, Shandor, and also thanks to all of you for listening.